Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, Oscillators and Amplifiers. This module deals with adder, subtractor, integrator and differentiator. So, these are the applications of the operational amplifier. And in the first lecture, we have discussed already that why the op-amp is called so. Because of these reasons, it is used to perform addition, subtraction, integration, differentiation, logarithmic and logarithmic functions. So, it is used to perform all these arithmetical operations, so it is called as operational amplifier. First, we are going to see about the adder circuit. When you see this circuit, the inputs are three. Three inputs are given to the inverting input terminal of the operational amplifier, and since it is an amplifier, it has got a feedback through the resistance RF and the positive terminal is grounded. So, you can call this circuit as a inverting adder circuit because the inputs are added here and the sum of the inputs V1, V2, V3 is given to the negative terminal of the operational amplifier, and so this adder is called as an inverting adder circuit. Instead of giving the inputs to the negative terminal, if you give the inputs to the positive terminal, this circuit is called as non-inverting adder circuit. So, this point is virtual earth summing point. Why it is virtual earth is this positive terminal is grounded, the potential here has to be, the difference between the potential at these nodes has to be 0. So, this terminal has 0 voltage and so this terminal is also assumed to be 0 voltage. So, here V1, V2, V3 are given to this node and at this node these voltages are summed up and the sum of these voltages are given to the negative terminal. And what is the output of this circuit? Output is nothing but the operational amplifier negative feedback circuit has got the gain as minus RF by Rn. Rn is the external resistance given to the operational amplifier, and if these Rn are equal, then RF by Rn is the gain factor of this operational amplifier and the output of the circuit will be sum of these inputs into the gain. So, V out is equal to minus of RF by R1 into V1 plus V2 plus V3. This is the output of the circuit, and if we choose the values of the resistance RF and R1 are equal, then the output will be the sum of all these voltages. We can add more number of input voltages since this point is assumed to be virtual ground, and this is all about the adder circuit, an inverting summing amplifier. It is otherwise called as inverting summing amplifier. And next is, when you see the circuit, you can tell what is the amplifier it is. It is a non-inverting summing amplifier or a summer. So, here why it is called as non-inverting summer? Because the voltages V1, V2, V3 all the voltages are summed up and given to the positive terminal of the operational amplifier, and always the portion of the output is fed back to the negative input terminal through the resistance RF. Here it is given as 2 kilo ohms, and this is the input resistance R1 which is connected to the negative terminal and the other end is grounded. So, here what is the output of the voltage for this non-inverting summer is, you have to recall the gain of the non-inverting amplifier as 1 plus RF by R1. Here it is 1 plus 2 kilo ohms by 1 kilo ohms into sum of all these voltages V1 plus V2 plus V3. So, this is the output of the non-inverting summer. So, in general the output is given by the gain of the non-inverting amplifier into the sum of the input voltages. So, if you want to have the output as only the sum of the input voltages, you have to design these resistances such that the output is equal to V1 plus V2 plus V3. Also, you can design the resistances connected in the circuit in such a way that this circuit can be an averager. Averager is nothing but the output voltage is the average of what are all the inputs given to the non-inverting or inverting amplifier. Here V1, V2, V3 are given. So, the output for the averager is calculated as V1 plus V2 plus V3 divided by 3. So, how you will get this output? By choosing the values of the resistances connected to the circuit. And next is subtractor. Subtractor, you need to have two voltages applied to both the terminals, positive as well as negative terminal. So, VA is the voltage applied to the negative terminal of the op amp and VB is the voltage applied to the positive terminal of the op amp. And again the output of the operational amplifier is fed back to the negative terminal through the resistance R, and for the both the input voltages the input resistance is connected and assumed to be equal. So, all the resistances are equal here and the output voltage will be the difference between the input voltages which we have applied to both the input terminals. So, it is VB minus VA. Why minus sign is given for VA is connected or given to the negative terminal of the operational amplifier. So, it is basically it is a differential amplifier. By selecting the values of these resistances, you can design a circuit as an amplifier, otherwise you can design a circuit as a subtractor. In an amplifier, if these resistances RF is higher than the input resistance, then it is an amplifier. If all the resistances are equal, then it will be cancelled out based on the gain of the differential amplifier, then it is a subtractor. You can also design an operational amplifier as both adder as well as a subtractor. It can perform addition as well as subtraction simultaneously for the given inputs. So, here VA and VB both are summed up at this node and it is given to the negative terminal of the operational amplifier, and VC, VD both are summed up given to the positive terminal of the operational amplifier. Again there is a feedback given to the negative terminal, and here this is the resistance called or compensation, which compensates the effect produced by the input bias current, which we have seen already in the previous session. So, here VA, VB is given to the negative terminal, VC, VD is given to the positive terminal, and irrespective or if do not bother about these resistors, what may be the output of this circuit? In general, it is the output is given by VC plus VD minus of VA plus VB, because these two voltages are summed up at this node and A, B voltages are summed up at this node, and the sum of the voltage is given to the negative terminal and positive terminal respectively. So, if you did not consider about these resistors, values of these resistors given in the circuit, you will get the output as VC plus VD minus of VA plus VB. This is the voltage you will be getting from this circuit, and so it is called as adder as well as a subtractor. It is performing addition as well as subtraction simultaneously by a single circuit. And next, this is a differentiator. So, we are going to see about the output of the differentiator and how the differentiator is going to perform for various frequency signals. So, it is basically active differentiator since it got an amplifier in the circuit, and here this is a passive differentiator with the help of only the capacitor or a resistor. Otherwise, instead of a capacitor you can have an inductor with the resistor. It can also perform differentiation and it is a passive differentiator. We are going to see about the active differentiator circuit, here the signal is given to the inverting terminal of the operational amplifier through the capacitance C, and the feedback is given through the resistance R to the negative terminal of the operational amplifier. So, for this circuit we have to derive the gain of the circuit. So, again I will draw the circuit. So, you have a capacitance at the input side and a resistance at the feedback side. Say this is C1 and the feedback resistance is RF, and signal Vi is given to the negative terminal of the operational amplifier. This is simply grounded. The positive terminal is simply grounded, and we know that these voltage Vd, the difference of the voltage between these two terminals is 0, since the terminals, these nodes are virtually grounded. So, here this node is considered as A. At A you have to apply a KCL, that is Kirchhoff's current law. This current flowing through the capacitance plus the current flowing through the resistance RF is equal to 0. So, the current flowing through the capacitance is given as Ci dVi by dt plus V naught by RF is the current flowing through the resistor, RF is equal to 0. From here calculate the output. V naught by RF is equal to minus Ci dVi by dt, and V naught is RF Ci dVi by dt. So, from this equation you can say that the output is the derivative of the input. And what is this RF and Ci? This is the time constant of the derivative factor, or this many times the input voltage is differentiated by the circuit differentiator. And if you go with the phasor notation, you will be having, or in S domain you will be having V naught of S by Vi of S is equal to minus RF Ci. Instead of the differentiation, I can give S in the numerator. Since we have Vi in the left hand side, we need not to have it on the right hand side also. And if you take modulus, I can say V naught by Vi as V out by Vi as the gain of the differentiator, and if you take modulus and after putting S is equal to j omega, you will be getting minus j omega RF into Ci inside the mod, and you can write it as omega RF Ci, and for omega if you put 2 pi f RF Ci, you can again rewrite this as f by Fa, where Fa is equal to what? 1 by 2 pi RF Ci. This is the gain of the differentiator. Now, if f is equal to Fa, what happened to the gain in mod? It will be 1. If you calculate it in dB, it is 0 dB. So, for the frequency response, you know that in x axis the frequency of the input signal, and in y axis the gain of the differentiator in dB, and for f is equal to Fa, that is the input frequency is equal to this Fa, what happens to the gain? Gain is 0 dB. So, consider this is 0 dB, and here this is your Fa. And if the frequency is increased, if the frequency of the input signal is increased based on the equation, what happens to the gain in gain of the differentiator? It will also increase, and it will increase at the rate of plus 20 dB per decade, and it goes on. So, at one point the circuit will break, or you can see that oscillation will be the output of the circuit. So, this is the problem in the differentiator. So, if the input signal's frequency is increased, then the gain of the differentiator also increased at the rate of plus 20 dB per decade, and this is one of the problem. And next problem is, in the higher frequency, the capacitance C, this capacitance is inversely proportional to the frequency, and so if the frequency is high, the capacitive effect is very low, and this system is sensitive to the noise. And these are the two disadvantages we have seen in the basic differentiator, and so we are going for the practical differentiator. We will see it after the break. Welcome back. So, we have seen two problems faced by the basic differentiator. One is, at high frequencies the input capacitance effect is reduced, and so the system is sensitive to noise. And another problem is, if the frequency is increased, then the gain of the differentiator also gets increased at the rate of plus 20 dB per decade, and at one point it will oscillate, it begins to oscillate. So, we have to eliminate these two problems, and so we are going for the practical differentiator circuit. And here this is the practical differentiator circuit, in which say what is the difference in the circuit between the practical differentiator and the basic differentiator. In the input side we have included a resistor, and at the feedback side we have included a capacitor. So, for that again we have to calculate the gain of the differentiator for the practical circuit. So, what is ZF? That is the parallel combination of the resistance and the capacitance, and what is Z1 is the series combination of R1 and C1. So, for ZF, if we calculate it, it is RF into 1 by CFS divided by RF plus 1 by CFS. So, it will be finally RF by RF CFS plus 1, and this CFS here, if you take LCM, CFS will get cancelled, and this is now ZF. And what is Z1? It is the input impedance R1 plus 1 by C1s. It has given us R1 C1s plus 1 by C1s. So, the gain is given as minus RF by 1 plus RF CFS divided by R1 C1s plus 1 by C1s, and this will be minus RF C1s by 1 plus RF CFS into 1 plus R1 C1s. So, this can be written as minus RF C1s by, if this RF CF is equal to R1 C1, the product of RF CF is equal to R1 C1, you will be getting 1 plus R1 C1s the whole square, and can be written as minus RF C1s by root of 1 plus R1 C1s the whole square if you take mod. So, this can be given as again rewritten as 1 plus F by FB. So, the gain of the differential amplifier for the practical circuit is given as RF C1s divided by 1 plus JF by FB the whole square. So, for the basic differentiator circuit, we have seen at 0 dB the frequency Fa is equal to F 0 dB, the gain is touched at this Fa, and if the frequency increases, the input frequency increases, the gain is also getting increased, and that is the problem we have seen. If it increase at one time, it breaks into oscillation. And now if we calculate the gain with the practical differentiator circuit, you have the term F by Fb here, and here Fb is always greater than Fa. So, you have to design the resistors and capacitors in such a way that this Fa is less than Fb and Fb is less than Fc, and we will see what is Fc in later. So, here if the frequency is less than Fb, that is here from here, if the frequency is less than Fb, the gain is increased at the rate of plus 20 dB per decade, and if the frequency gain is increased, if the frequency is greater than Fb, after this Fb, if the frequency of the input signal is increased, the gain will decrease at the rate of minus 20 dB per decade as per this equation. If this numerator is increased, so if it is increased beyond this Fb, this term will be a higher term, and if you divide this term by a higher number, then the gain of the differentiator will become reduced, and it is at the rate of minus 20 dB per decade. So, now we have seen a problem in a basic differentiator circuit which is eliminated by this practical differentiator, and also in the input side of the differentiator we have included a resistor. In the case of the basic differentiator, we have only the capacitance. If we introduce a resistance in series with the capacitance, then at the higher frequency, these two impedances, that is the resistance and the capacitance, will make a higher input impedance, and so it is immune to noise. So, these two problems faced by the differentiator in basic is eliminated with the help of this practical differentiator circuit. And what is this Fc? Is this Fc is this frequency Fc. This is the open loop response of the operational amplifier, and this Fc is called as unity gain bandwidth, or otherwise you can say that the open loop response touches this 0 dB is said to be the frequency Fc. So, always we have to choose this Fa less than Fb and Fb is less than Fc. And how the differentiator should be designed? A good differentiator may be designed as per the following steps. Choose Fa equal to the highest frequency of the input signal. Assume a practical value of C1 less than 1 microfarad and calculate what is RF. So, we have the equation what is Fa, in which Fa is decided by the capacitance C1 and RF. C1 is assumed and RF easily can be calculated, and choose Fb is equal to 10 times Fa and calculate the values of R1 and Cf, so that R1 C1 is equal to RF Cf. So, by these two steps you can design a good differentiator and you can reach the desired result. And next is integrator circuit. So, if we interchange the resistance and the capacitance connected in the differentiator, you can get a integrator circuit. In the differentiator, at the input side you had a capacitor, and now the integrator you have a resistor at the input side, and in the feedback side in the differentiator you got a resistance, now it is a capacitance. So, what is the output of the integrator here? It is minus 1 by R1 Cf integral Vi of t into dt. So, here the input which is the the output is the integral of Vi of this times 1 by R1 Cf. And why this minus sign here? Again the input signal is given to the negative terminal, and so there is a 180 degree phase shift between the input and the output. As the gain of the integrator decreases with increasing frequency, the integrator circuit does not have any frequency problem as faced in the differentiator. How can you know that? So, again we have to discuss about the gain of the integrators. So, gain of the integrator circuit is derived as V naught of S by Vi of S is derived as 1 by omega R1 Cf. So, here this A is given as Fb by F modulus. So, here the practical problem of the basic integrator is at this Fb, or otherwise you can say if F is equal to Fb, the response touches this 0 dB, and at omega equal to 0, the gain of the integrator is infinite. Actually, practically it is infinite based on this formula. If omega equal to 0, then it will give you infinity. So, this is one of the problem in the integrator. So, we are going for the practical integrator. In the practical integrator, you are connecting a resistance across the capacitance in the feedback circuit, and by which you will be having actually in the low frequency you will feel that this capacitance effect is nil. So, there will be a open circuit. So, you will be having no loop across this 2 points. So, if there is no loop in the basic integrated circuit, then it will act as a open loop configuration. So, your output instead of infinity, your output will saturate. So, that is the problem faced in the basic integrator, and so we are connecting a resistance across the capacitance, and if you connect the resistance across the capacitance, then there will be a loop even though there is a open circuit across the across this path, capacitance path at the frequency 0. So, because of this resistance at frequency 0, you will be having the gain as minus R2 by R1 based on the inverting amplifier design. And if the frequency is increased, the gain is getting decreased at the rate of minus 20 dB per decade. If the frequency of the input signal is increased, the gain is getting reduced, and at this frequency based on these two components, you will be having a frequency term, and at this frequency this gain is reduced by 3 dB. So, that is the cutoff frequency of this circuit. So, the problem faced in the basic integrator is also reduced by having a resistance connected across the capacitance, and so your frequency response is not saturated when the input frequency is 0. It is instead of saturation you will be having minus R2 by R1 here, and it is the gain is reduced, not as in the case of the differentiator. And this is about the practical differentiator circuit. So, these are the frequency terms you have to follow for the practical integrator circuit. And now the summary of this session is we have seen the adder, subtractor, adder as well as a subtractor, and the problems faced by the ideal integrator circuit and how it is eliminated, and the problems faced by the differentiator circuit and how it is eliminated. And questions to check your knowledge: what is an adder, what is the use of the practical integrator, and list the disadvantage of the differentiator. These are the references. Thank you.